All right, hey, I said I'd try to make a video, so here I go. I hope somebody watches it and gets some use out of it, but these first few problems I'll try to go pretty fast because I think you've got the gist of these and I know we went over them in class, but here goes. So looking here again, the whole point of this quiz is to find these chunks of area that are found between two functions. And you got to take a couple steps when you're doing that. The first step is to find the points of intersection. I'm going to write these steps out because I don't think I ever really did, but let's do that. Find points of intersection. And hopefully it's obvious to you that the way that you find the points of intersection is you take the two functions, set them equal, and solve algebraically. So, in this problem we've got a function called f and we've got a function called g. And if you take the two expressions and set them equal and solve, then you'll get the points of intersection. Those points of intersection then become the limits of integration of your integral. So we can see that this first chunk of area lives between points A and C. So those would be two of the values you get if you set these functions equal to each other and solved. You'd get A and C. You'd also get D, but D is the endpoint of a whole second integral. So you go plus, you need a second integral now that goes from C to D. But that's obviously an important step here. So you set the functions equal. Another important step in setting up your integral is determine which function is greater on which interval. And what I mean by that is literally which one gives the greater y values. So between A and C, you'd pick some value. Obviously 0 is in the middle, and hopefully obviously when you plug in 0, f is giving a greater y value than g is. So you know that on this interval, you'd want to set up your function such that you're doing f of x first and subtracting g of x from that. So in our little integral, the integrand should be f of x minus g of x in that order. You want to make sure you're setting it up so that when you're subtracting, you're getting a positive value. So you got to do big guy minus little guy. And then of course you need the dx on the end. But as we slide over into this other interval between c and d, you'd pick some x value, I don't know, that one, and you can see that this time it's actually function g who's greater and function f who's less. So this time our integrand would be exactly the reverse of what we had before. This time you're going to want to go g of x first minus f of x. And of course put a dx on the end. And then that's the whole thing. When I say write an expression using integrals that represents the area, then because there's two different chunks of area, you need two different integrals. Those integrals should be getting added together, but the functions inside the integral should be getting subtracted from one another. So just keep it straight, you'll be fine. But to answer these previous questions, which function is the higher function or the greater function from A to C? We already said that's f. And which function is greater on C to D? We said that's g. That's it. That's number one. To finish my list of steps for a problem like this, determine which function is greater. Step 3 is set up inequality. Set up integral. And set it up, complete with limits of integration, complete with making sure that you've put the functions in the right order, right? F minus g versus g minus f. Step 4 is, I want to just say solve using Fundamental Theorem of Calculus, but maybe we need to break that down. Solve using FTC. So there, your little sub-bullets would be, first you're going to find the antiderivative. And then step 2 is just plug in the upper limit of integration. So if you were doing the integral from a to b of little f of x dx, then we said your antiderivative is big F and you're going to plug in b first, and then just subtract from that big F of a. And that should give you your answer. You just find the antiderivative, plug in b, plug in a, subtract, and whatever answer you get out is your area. That's it. Next, this question about sine and cosine is basically the exact same deal. Again, you see that there are two chunks of area, so you should be expecting the area to be one integral plus a second integral. The first integral is going to go from 0 to pi over 4, because that's their point of intersection. The second is going to go from pi over 4 to pi over 2. They both need dx's on the end. And the first integral, in the first integral, it's the cosine function that's the greater function. So our integrand is going to be cosine of x minus sine of x in that order. And the second guy is going to be sine of x minus cosine in that order. Rats. Alright, I didn't plan ahead super well, so those aren't fitting, but that's the answer. And you don't have to do any more. It literally says do not evaluate. So I'm not expecting you to actually use the fundamental theorem of calculus where you have to find the antiderivative and substitute in. We're not doing that. You just set the thing up and move on. So if you're really desperate to actually solve, then number 3 is the first one where you have to actually find the area. So we'll talk about that in 1 second. Okay, so for this problem, I wanted to give you a grid and really give you a chance to kind of walk through the process of thinking about which function is which and where do they intersect each other. So you really should be comfortable with the fact that x squared minus 3 is just a parabola that's been dragged down 3 units. So if a parabola normally had its vertex at the origin, then this one has been dragged down 1, 2, 3. And if a parabola normally passed through the point 1, 1, then you just drag that down 3. And basically we're over 1, up 1 from here, getting these 2 points. For a parabola, 2 would have normally given 4, so over 2, up 4. So same thing from this vertex, we'll go over 2 and up 4, 1, 2, 3, 4. And we can bounce that guy over the axis of symmetry, which is just the y-axis. Again, if we were graphing plain old x squared, you'd expect 3 to map up to 9. So from here we could go over 1, 2, 3, and then just go up 1, 2, 3, 4, 5, 6, 7, 8, 9. We would be right there. We could bounce that over 1, 2, 3, 1, 2, 3, use symmetry. And then there is a good looking graph of our function. This is not super easy to draw on a stylus, on a tablet with a stylus. Oh, that was horrendous. All right, I've seen better graphs, but I can live with it. The next function is just a line. Please tell me you can handle a line. If I see negative 2x plus 0, then I know I'm passing through the origin. And the negative 2 tells me my slope is down 2 over 1, and whoops, I get a point of intersection for free. And then I'm down 2 over 1, and I'm down 2 over 1. And if I go up 2 over 1, I get a point. And if I go up 2 over 1, I get a point. And if I go up 2 over 1, then whoops, I get another point of intersection for free. So that's kind of on purpose, as I wanted to give you a problem that was fairly easy, where you can just clearly see that the points of intersection here are negative 3 and also 1. So setting up our integral should be pretty easy. We know that we want the integral that goes from negative 3 to 1. And we can literally see that the greater function between negative 3 and 1 is the line. So as we set up our integrand, we will go negative 2x first. And then we'll subtract from that the red quadratic function, so x squared minus 3. And again, if you remember anything, please remember to check parentheses around this so that you remember that the negative sign distributes, and also to put a dx on the end. But there's your integral. Again, if this question said, hey, just write just write an expression, then you'd be done. But basically that expression represents this area right here. But we're not done because we weren't just writing an expression. We are expected to actually find that area. So to do that, we should simplify this equation or expression, and then we should find the antiderivative. So this is still the integral that goes from -3 to 1, but I'm going to clean up this function. I'm going to let this negative distribute, so I get negative x squared, then minus this 2x in the middle, and then the negative distributes onto the 3, giving me a positive 3. This is all dx. And then I can handle this function as is. So let's do it. Do I bother? I don't know. Part of me wants to say, hey, do you want to factor out a negative? Because if you want to, you could. If you factor out a negative to have x squared minus 2x plus 3, then you could do another little trick where we flip these limits of integration, go from 1 to -3 instead. That would generate another negative on the outside, right? And we know that we're allowed to take constants like this -1 and pull them out. And then these two negatives would cancel. And then if you really wanted to, you could do an integral that kind of goes backwards from 1 to -3 of a function that doesn't have a negative leading coefficient. But have we really saved anything by doing that? First of all, I screwed it up. If you factor out the negative, then this goes... Here we factored out the negative, so this would go to plus, and this would go to minus. Have you saved yourself anything by doing that? Not really. But if you think this expression is maybe a little cleaner and easier to work with, then you could do that. You know, it's a trick I did do on a later problem. It's probably not worth it here, though. But I digress. Let's keep going. To actually evaluate this, we need our antiderivative, and our antiderivative would be an x to the power of 3, which I then need to multiply by the reciprocal, so I get a coefficient of 1/3, but that's it. Then this guy's going to go x to the 2, and technically I've got a coefficient of 2, but I'd multiply by 1/2. It would all cancel. You just want x squared. Then you go minus 3x. Then you do the vertical line thing, and you transcribe your limits of integration onto that vertical line thing. And and you throw parentheses around everything. And then you evaluate this by substituting in, right? Now I've switched the limits of integration, remember? So I'm still throwing in what is, for me, the upper limit. He's still the guy that goes in first. So I'll go 1/3 times a -3 cubed plus a -3 squared minus 3 times -3. And all that's just the first bit. Now I need to subtract from that what I get when I plug in 1. So that'll be a 1/3 times a 1 cubed plus a 1 squared, which is 1 minus 3. I'm going to cheat a little bit because I can see I'm running out of space. But now we evaluate. So I'm looking at -27, and 1/3 of -27 is -9. Then I'm looking at a +9, so those will very conveniently cancel. Then I'm getting another +9. And over here I'm getting what? 1/3 take away 2. 1/3 take away 2. That feels like -1 2/3 to me. Alright, like I said, these 9's cancel, but I've got a 9. This guy over here is thirds, so 9 expressed as thirds would be 27 thirds. Minus a minus will be plus, so I'm adding 3, 4, 5 thirds. And that's coming out to 32 thirds, which I think is the answer we got in class when we did this problem. So I'm going to call it 32 thirds. I'm going to put a box around it and call that a problem done. That's 3. Let's try 4. So 4 says, find the area bounded by these functions. You should know how to find the points of intersection algebraically. If you can't find them, then use your calculator. So no, don't use your calculator. You need to be able to do this by hand. My expectation on the quiz would be that you can do this by hand. And if you just suddenly find the points of intersection without any work shown because you did it on your calculator, you should not expect to get credit. But the way we're going to do this is just take these guys, set them equal. So we'll go x cubed minus 9x. And you'll set that equal to 9 minus x squared. And the problem literally tells you how to solve this. It says factor by grouping. But before you factor by grouping, you want to get into standard form. So leave your x cubed over here on the left, and then add x squared to both sides. And leave your minus 9x over here on the left, but subtract 9 from both sides. Next thing you know, you got your right-hand side set equal to 0. Then we want to factor by grouping. Be careful with factoring by grouping, because you don't want to do this. If you have a negative in the middle, you need to leave that attached to the 9x. So you kind of have to force these guys apart and kind of jam a plus sign in the middle, because it should still be thing plus thing plus thing plus thing, if that makes sense. Anyway, once you've got everything grouped, you factor out the GCF, which is x squared, leaving you with an x plus 1. Then you get your plus sign. Then you factor out the GCF here. Now, if this leading guy is negative, then you need to factor out this common factor of 9 as a negative 9 to be left with x plus 1. And again, factoring by grouping doesn't work unless you get this same factor twice. Now, because we get that same factor twice, it just became a common factor. You can literally factor out the whole x plus 1. And if you factor that out, then you're left with this x squared plus a negative 9, aka minus 9, which equals 0. So this factors again. You have an x plus 1, and this difference of squares becomes an x plus 3 and an x minus 3. So it turns out these two graphs actually cross each other 3 times. They cross each other at negative 3, but also at negative 1, and also at positive 3. So to kind of better visualize that, what you've got going on here is you've got a cubic function in blue that's pulling one of these, bloop, and then you've got a quadratic function that comes running in like this, hits it here, hits it here, hits it there, and then goes back down. So you're getting 3 points of intersection, one here at negative 3, you're getting a point of intersection here at negative 1, then you get another point of intersection here at 3. That means when it's time to write your integral, you're not going to write me 1, you're going to write me 2, and the first one's going to go from negative 3 to negative 1, the second one's going to go from negative 1 to 3. And again, based on my drawing, I can tell which function is the greater function, but if you did not know who was greater, you'd just pick any number between these two values. And here, you don't have a lot of choice. You'd probably want to pick negative 2. It's the only integer between them. Between negative 1 and 3, you got some good choices. I mean, the obvious choice is to just pick 0, though, and see what happens. But again, if I plug in, I'm going to do f of negative 2. And f of negative 2 is negative 8 plus 18, so positive 10. And g of negative 2 is 9 minus 4, so only 5. So there's the proof that the cubic function, f of x, is the greater function, right? 10 is greater than 5. So on that first interval, you know that it's the blue function first. So our expression is going to be f of x minus g of x. Although I don't think you even had to write this. Oh yeah, you do. We have to do this whole problem? Well, I don't want to do that. All right, but minus g of x dx. And this other guy is going to be g of x minus f of x, because if we test this one, we're testing 0 this time, and f is giving 0, and g at 0 is 9. So this time, when we test, we see that it's g that's the greater function. So when we go to write our integrand, we're going to do g first. We're going to do g of x minus f of x. And put a dx on the end. But if you were writing your expression, then there's your expression. If you had to actually do this now, then we better plug in and do it. Did we do this in class? Can I just skip this? I guess let's not. Let's try to make sure we have it in the video in case someone needs it. But so what would this be? This would be the integral from -3 to -1 of f first, so the x cubed minus 9x, and then minus g, which is 9 minus x squared, dx. The second integral would be the integral from -1 to 3. But this time it's the 9 minus x squared going first. And we're subtracting from that the x cubed minus 9x. And that gets a dx, which you can't quite see, but that's okay. All right, let me scroll down, give myself a bunch of room. Too much room. Okay, move this thing back down here. Move this thing back down to the bottom. Okay, nothing but room now. So what are we doing? We're doing an integral that goes from -3 to -1 of this thing. Let's clean it up. It's an x cubed plus an x squared, and then minus a 9x and minus a 9. That's dx. Now we know that this other integral that goes from -1 to 3, it's going to be the exact same integrand. It's just going to be the opposite because the order was reversed. So really you could just take this whole guy and just go negative x cubed minus x squared plus 9x and plus 9, because you know it's going to be the same thing just with the opposite signs. Now this is that trick I was saying before. If you wanted to change all these signs, couldn't you just change the order of the limits of integration again? Just integrate from 3 to -1. That generates a negative. You could then distribute that negative throughout this whole integrand. And now you literally have the same function in both integrals. Now there's no way to combine the two integrals, so it's not super useful, but it might be nice to just find your antiderivative and be able to use the exact same thing, not even have to change the signs, right? So I'm gonna do that. It's not the most useful thing in the world, but it seems kind of good. So let's do our antiderivative. I'm getting x to the 4th with a coefficient of 1/4. I'm getting an x cubed with a coefficient of 1/3. Then I'm getting minus an x that is squared with, I already had a coefficient of 9, so my coefficient now will be 9/2, and the 9 just becomes 9x. And of course, I need to evaluate this whole thing on the interval that goes from -3 to 1. And then I got to add to it the exact same antiderivative. So again, 1/4 of x to the 4th plus 1/3 of x to the 3rd minus 9/2 x squared minus 9x, evaluated from, this time 3 to -1. All right, nothing left to do now but plug in and do this math. So plugging in 1 gives me 1/4 plus, now again, my little tablet likes to take 1/4 and make them look like 1/9. So just remember that's 1/4. I get 1/3. I get 9/2. And I get 9. That's what I get when I plug in 1. Now I'm going to subtract from that what I get when I plug in -3. So I get 81/4. Oh, exhausting. All right, 81/4. Then I get -27 times the 3rd is -9. I think that's right. Okay, this goes in, I get 9, I get 81/2. And this goes in and I get plus 27. Okay, and all that is only the first integral. Now we do it all again. But notice what? Oh no. Okay, I screwed up. This 1 is supposed to have been a -1, which means when we plugged it in here, it stayed positive, but when we plugged it in here, we should have gotten a negative. When we plugged it in here, it stayed positive, so we get a minus. Here, though, we should have a plus. Okay, other than that, no big mess. But we already plugged in -1 and got all this stuff. We're about to plug -1 in again into the exact same expression So can I just borrow all this crap again? Yes, I can. So it's 1/4 minus 1/3 minus 9/2 plus 9. And that should be the exact same thing we got over there. Now this time over here, we're plugging in a positive 3. So it won't be exactly the same as what we had here, but it should just be off by just a couple of signs. So a positive 3 here gives 81/4. And a positive 3 here gives positive 9. And a positive 3 here gives us minus 81/2. And a positive 3 here gives us minus 27. Okay, we got all the numbers out. Now just crunch these. I don't super want to do this. I feel like I cheated when I made the answer key and just put all this in the calculator. So let's do that again. You guys have your calculator, and this is the kind of thing that I don't mind you using it for. So turn on calculator. Boom. Share calculator. There it is. I'm hoping you don't need to actually see the buttons I'm pressing. I think you can just kind of look at the screen here. But I'm going to do 1/4, so 0.25, minus 1/3, minus 4.5, plus 9. So I'm getting a decimal. You guys know I'm not into that, so I'll go math frac and convert that to 53/12. And the cool thing about that is, that means this guy is also 53/12. All right, and then back to the calc. We're going to go 81/4 minus 9 minus 81/2, which is 40.5, plus 27. Hopefully that worked out fine, but I'm a little paranoid because I didn't put parentheses around this. I think it's fine though. Yeah, okay. So that is, of course, math frac 9/4, negative 9/4, I should say. So it's minus negative 9/4. We'll clean that up in a sec. What's happening over here? Minus. I gotta do this one. What's the difference here? You were a negative 9 and you're a plus 27. So it's like we're adding 18 but taking away 54. Add 18. Take away 54. Alright, I'm getting that. Negative 153/4. And if my tablet could just let a 4 be a 4, that would be great. Alright, so what's all this? Well, you're 27/12, and I'm adding you. So 5, 6, 7, 80. This does not feel right. 80/12, which is really 40. 1/6, which is really 20. 1/3. All right, what's this guy? Times 3. Oh, I don't feel good about this at all. All right, that's that guy. Then we are adding on 53/12 plus times 3, 3, 4, 59 twelfths. Oh boy. All right, so what are you? You're 80/12. Go back to being 80/12. And then we're going to add on, oh God, 512/12, which according to me is 592/12, which according to the calculator is that thing. 148/3. I think that is right. I think that is what I got. All right, so good. Maybe that's fine then. Is now the best time to maybe show you how to do this whole thing on the calculator? I'm going to say yes. So if I scroll way back to the top, what would it look like if we did this whole thing on the calculator? Well, obviously step one is to plug in the functions. So cubic function goes first, and the other guy next, 9 minus x squared. You could hit graph on these. There they go crossing each other. I'm hoping you remember that to find the points of intersection, you're hitting second and then calc right above trace. And you're choosing option 5 for the points of intersection. So your first curve is the blue cubic, press enter. Second curve is the red quadratic, press enter. And your guess is just to be close to a point of intersection. Pressing enter, you see we're getting 3. Now we already did this algebraically, so you guys kind of know the deal. I'm not going to find the others because we know what they are. Here's what I will do though. I will say that if we wanted to find the difference in the areas between them, we could make a third function where we go vars, and this part maybe you want to see, so let me maybe bring that up. Alright, see that button down? No, you don't see it yet. Boom. Now you see it. See this button that says vars? You're pressing that. So vars. And then you go to the right to get to the submenu yvars, and then you want a function variable, so press enter on that and choose y1. Maybe I'm about to do this backwards, but that's okay. Now go minus and do it again and go vars, yvars, function vars, and choose y2. And I'm now doing blue minus red. And blue minus red is what I wanted for that first interval, right? The one that goes from -3 to -1. So now you might want to turn the other functions off by highlighting the equal sign and pressing enter. Now if you hit graph, you only see the one thing, and I want that first chunk of area. So I'm going second calc, choosing option 7 for the integral, and my lower limit is -3, I press enter. My upper limit's -1, I press enter, and I'm getting 6.666. And remember that number because we already found that number right here when we got 80 over 12. Because guess what 80 over 12 is? $6.666. So we know that we evaluated that first antiderivative correctly. Now for the second one, technically we've got the wrong function. On the second interval, the one that goes from -1 to 3, we should be doing y2 minus y1. But let's use that same trick of just reversing the limits of integration. So I'm going to go second calc, option 7, and I'm going to use the same sort of light blue colored function. Now it's technically wrong because it's y1 minus y2, but that's just the opposite. So for your lower limit, use the +3, and for your upper limit, use the -1. And now because we reversed our limits of integration, we'll get the opposite answer, but since our function was backwards, we'll get the right answer. So shade, 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 you're getting 42.666, which should be the 512 over 12 that we already got. So second quit, 512 over 12. Look at that, it's the same right answer. So combining those would give us our total area, which would be what? 48, 49, and 1/3. Yeah, 49 and 1/3. Which is 148 over 3, right? I don't think so. Yeah, perfect. I never doubted myself. Obviously that was all perfect. Okay, great. This took super long, and I don't want to do any more of these ever, but maybe we can do one more. All right, find the area by the functions below. All right, again, just to kind of walk you through. You'd graph these functions to find the points of intersection, but you have to know how to do it by hand too. But just again, to give you a heads up, you can totally type in the x plus 7 and the x squared plus 2x plus 1 and graph them and get a look at it. And you can see we've got a parabola intersecting a line. Certainly looks like that's happening at -3 and +2. But let's show the algebra and make sure that really makes sense. So turn this calculator off, give ourselves room back, and do this math. Alright, so grab the line, x plus 7, set it equal to the quadratic, x squared plus 2x plus 1. And get that thing set equal to 0. So your x squared's fine, but we're going to subtract x, so we just have plus 1x. We're going to subtract 7, so we just have minus 6. And then that's factorable. So you get x plus 3 and x minus 2, which means the 2 points of intersection are exactly the points that we thought we saw in our graph. They're at -3 and they're at 2. And that means our integral should be an integral that goes from -3 to 2. And I saw on the graph, maybe you remember, or maybe you need me to bring it back. Zoop. I saw on the graph that the line function, the linear function, had the greater values on the interval that we care about. But again, since you have to, absolutely have to show your work, I'll show you how to do that again. Since we're integrating from -3 to 2, you can just plug in any value on that interval you want. You'd be a fool to pick anything other than 0. So you test f of 0, and it's clearly 7. You test g of 0, and it's clearly 1. So guess who wins that battle? F does. So we know that f is the greater function, f being the line. So set up your integral with the linear function first. X plus 7 minus x squared plus 2x plus 1. Slap a dx on the end. Slap some parentheses around this guy so you don't forget to distribute this guy. But then we're basically ready to get to work. So we've got an integral now going from -3 to 2. Clean this up and you get a negative x squared plus 3x plus 6. That feels wrong, because it is wrong. What I meant to say was we get negative x squared, then we get x minus 2x, that's minus 1x. And then we have 7 minus 1, which is 6, so that part's fine. Okay, so this time I won't mess around with the limits of integration. We'll just deal with the fact that there's a negative in the front. It's not like it's that hard. But again, this guy, his power wants to go up to 3, which means I now need a coefficient of -1/3. This guy's power wants to go up to 2, so I need a coefficient of 1/2. And this guy just wants an x on him at all, so it's 6x. And we'll evaluate from -3 to 2. And again, these numbers should be small enough that you can do this by hand. So a 2 cubed is 8, so you get -8/3. Minus a 2 squared is 4, and half of 4 is 2. And 6 times 2 is 12. So there's that. Then we're subtracting from that what we get when we plug in -3. So -27 times a -1/3 is a +9. That's kind of happening a lot. This is 9/2, minus 9/2, and then minus 18. But that's it. This is the whole thing. So these two guys just make a 10. So we're doing -8/3 plus 10, and 10 is 30/3. So if we finish evaluating all this, we're going to land on a 22/3. Then if we evaluate all this, this will be a -9/2, and the 9 minus the 18 will be another -9. But that 9 becomes 18/2. And it's minus minus, so we get -27/2. And of course we're trying to subtract these two things. And minus minus means we're adding. And I guess I want a common denominator. So times 2 is 44/6. Plus times 3 is 81/6. which together makes 1/256. And that's that answer. But again, not to be outdone. Let's take a look at the calculator. Yoink. All right, and again, the functions are already in there too. So if you've already got them in there, and if the y1 is the greater function, then just put in another function that is y vars function vars to y1 minus y2 vars y vars function vars 2. All right, and then it's that third function that we want. Don't delete the other ones, but turn them off if you care to. Then hit second graph. And basically we're looking for the area under this thing. So we'll go second calc, option 7. We're going from -3 to +2. And we're getting that, 20.8333. And I bet it's no shock to find that 125 over 6 is 20.833333. So we know we got that one right. Our calculator verifies, but our algebra is what's worth the points. Wait, is that all I gotta do? Oh man. Oh man. Okay, cool. I can bring the calculator back more easily now. All right, page the next, number 6. I don't think I'm doing this. Oh, we only have to write the expression. All right, fine. I'll go through it. You guys will fast forward through it because you don't care, but that's okay. All right, what are we doing? We're going to set these equal. So x squared plus 10x and x cubed minus 3x squared minus 50x. Setting these guys equal. You've got a cubic over here, so I'd bring everything else over to him. And you're going to end up with an x cubed. I've already got -3x squared. I'm going to take another one away, so -4x squared. Then I've already got 50 of these. I'm going to take away 10 more, so that goes to -60. And immediately I see that everybody's got an x in common, so I'll factor that out. And then this guy is pretty obviously factorable. 6 times 10 is going to give you 40. And 10 minus 6 is going to give you 4. So I guess I want an x minus a 10 and an x plus a 6. And that should make everything work out, which means the 3 points of intersection of these two graphs are -6 and then 0 and then 10. And that means that the expression that models our area would be an integral that goes from -6 to 0 and then plus an integral that goes from 0 to 10. And again, we just have to know which function is greater. So from -6 to 0, I guess I'm plugging in -1. And -1 is giving 1 minus 10, so -9. And -1 down here is giving -1 minus 3 plus 50. So that's what? Positive 46. All right, so that one n wins by a mile. So we're going to do n minus m dx. And the other one should be the reverse. I mean, typically the sign is gonna change, but it doesn't have to change necessarily. So run your test points. Between 0 and 10, you're plugging in +1. And +1 is giving 1 plus 10, which is 11. And +1 down here in function n is giving 1 minus 3 minus 50. So that's -52. So for sure, 11 is greater this time. So this guy wants to be m minus n in that order with a dx on the end. And mercifully, we're not being asked to actually solve this one. They're just being asked to set it up. So there's your expression. It would be the sum of these two integrals. And finally, we get to 7, 8, 9, and 10, which are all a little bit different. You don't have polynomials anymore. You have radical functions and logarithmic functions, and maybe there'd be an exponential also. But I'm telling you, you can totally do this whole problem in the calculator, which means you don't really need to do any algebra. So bringing up that calculator again, you're going to go y equals clear, clear, clear. You're going to plug in the ln of x. and you're going to plug in negative root x. And you're going to hit graph. And I can see that they do cross each other here. Now, what I can't do is show what this x equals 3 is doing. But x equals 3 is literally just a vertical line. So here's what I can show you. There's a secret third line here, right? Looking at just this graph, that's not everything. They gave us 3 functions, right? So they gave us the log, we got that. They gave us the upside down radical, we got that. But they also said x has to equal 3. And if x equals 3, then 1, 2, 3. That puts a vertical line right here. So that means that the bounded area that we're looking for is just this little chunk right here. So guess what? We're kind of close to done already because, yeah, I know that my integral is going to be zoop. I don't know my lower limit of integration because I don't know what that point of intersection is right here, but I know my integral has to end at 3 because of this function. And I also can see clear as a daisy, clear as a bell, that the ln function is the greater function and the radical function is the lesser function. So my radicand definitely wants to be ln of x first and then minus the negative root x, so just plus root x will suffice. That's a dx. So the only thing left for us to do is find this point of intersection, and honestly, if you had to do ln of x equals negative square root of x, that's going to be a pretty annoying equation to try to solve, but you don't have to. I said you could use your calculator, so bring that bad boy back and just go second calc, yeah, and choose option 5. First curve blue, enter. Second curve red, enter. My guess is sure right there, and I'm getting 0.0495. And no, you don't have to make any sense of that number. Just plug it in. 0.495, I hope is what I said. But there you go. There's your expression that would give us our area. Are we asked to actually find the area? Unfortunately, yes. So to do that, we go back to the old calculator. And while you've got x handy, you might want to save it. So we can go store as alpha a. I've now got that as a. But now I'm going to go into y equals, and I'm going to enter. This one's easy enough to just do. Like I could do the y1 minus y2 thing again, but let's just literally type ln of x. Minus minus meaning plus square root of x. And we know that we're looking for the area under that curve, so that one is the green one. So if I hit the graph, I want this green guy. I'm going to go second calc, 7. Now notice my calculator defaulted to the blue function. I don't want that. So press down, and it goes to the red. Press down again. Now you're on the green. Now that you're on the green, you can enter your lower limit, which was the 0.495. I'm just going to type the decimal, 0.495. Press enter. Our upper limit was 3. Press enter, and your calculator will very kindly do that math for you, showing you that the value of the integral is 4.371. So the area is 4.371. And that's it. That's the whole thing done inside of a calculator. And that's fine. You didn't have to do the algebra to find the points of intersection. You didn't have to do anything. This was all good. Let's do another. So looking at 8. Again, I've got a bunch of functions. Let's just plug them in. Go to y equals, clear out all this detritus, and start over. We're going root x. That's a function. We're going x minus 3. That's a function. Then we've got x equals 0. I can't graph that. That's a vertical line. But the y equals negative 2, I can enter that. Just literally go negative 2. That'll be a constant. If you hit graph now, you should see 3 functions all kind of just going nuts. And so I'll grab this again, drag it over, and I'll blow it up bigger. And I'll get rid of the calculator for a sec. And now that we've got this guy to look at, remember we did also have this boundary that said x equals 0. Well, x equals 0 is just the y-axis. But technically there should be another lavender colored line right here. And that thing is cutting us in such a way that we can see the area we want is here. Now it may not look like it, but this is two different regions because of where the green and the red intersect. Now they intersect at 1 fairly obviously. But that means to the left of 1, you want the area that's between the blue and the green. To the right of 1, you want the area that's between the blue and the red. So that's definitely two different integrals that you need to write. So let me grab this. And throw all this out. So here's our little sketch of what's going on. And from this sketch, oh, I forgot we need one more thing. We do need to know that point of intersection, the point of intersection of the red and the blue. So heading back to the trusty calculator, you're going to find that point of intersection by saying second calc. Point of intersection, which is option 5. Make sure you're on the right two curves now, because this, for the first time, we've got 3 different curves going. So I definitely want the blue. So if they're saying first curve is the blue one, you go yes, and you press enter. Second curve is the red one, you go yes please, you press enter. And then for your guess, go over to the point of intersection, press enter. So your intersection is 5.303. I'm going to go second quit. Make sure x is 5.303. I'm going to store that as A, so I can't lose it. Okay, got it. Second quit. Now, let's write this down before we evaluate it. The expression I'm expecting you to give me, again, you've got the 2 different regions, region 1, region 2. And region 1 just goes from 0 to 1. And on region 1, I want the area between blue and green. So the blue function is root x. And I'm going to subtract from that the green function, which is just y equals -2. So it's actually plus 2. But that's it. That guy gives me the total area of region 1. Then I want to add to that the integral that goes from 1 to that point of intersection that we found and that I already forgot, 5.303. We're going to use that as our limit of integration. So we're going to go up to the point 5.303. And again, in region 2 we can see blue is greater than red. So we want that same radical function, but we want to subtract from that the red function, which is the line x minus 3. In parentheses with a dx on the end. So there's your expression. And I don't even need you to simplify it. Just have it set up. And then you can go to your calculator to evaluate all these pieces. But how are we doing this? I might just make some secret option down here that just says root x plus 2. I don't know what I'm doing. Root x, close parentheses, then add the 2. If you hit graph now, you'll see that secret orange function come flying through, and you can go second calc, option 7. Remember, for that one we only wanted to go from 0 to 1, but again, make sure you're on the right function. I'm on the blue, now I'm on the red, now I'm on the green, now I'm on the orange. So now I can enter 0, 1, 0, enter, 1, enter. And I get this little sliver of area worth 2.6666801. I'm assuming that 801 at the end is round off error, and that really we're getting 2.6666666 repeating forever. I don't know that, but I think that. But I'm going to write down 2.667 either way and just be accurate to the thousandth. Don't forget I got to add to that this other guy. So let's just enter him as a function. So he's root x, but instead of plus 2, it's going to be minus the x minus 3. Hit graph, and there's the little orange function this time. Just do it all again, second calc, option 7. Make sure you're on the orange function, which is down, down, down. Press enter. I mean, don't press enter. Enter your lower limit, which for us wants to be 1. And our upper limit, you may remember we stored as a. That'll take us out to the 5.303 and give us an area of 6.823. Get this out of here. I said out of here. Perfection. 6.823. All right, so that means our total area is the sum of those two numbers that I don't feel like doing a summation of. So second quit, clear, 2.667 plus 6.823. 9.49. Okay, never want to do that again. But there you go. That's that area. Let's do this 2 more times. I don't want to, but we're so close to the end now. Let's do it. All right, so to do this all again, just clear all this junk out of your calculator. I want 3 root x, so just insert a 3. Then I want negative root x. So that's looking good. And then I want a vertical line at 4, which I can't generate, so too bad. But if you graph these two, it looks like this. Where'd that guy come from? I didn't delete him? My bad. Okay, graph this. This can go in the trash. And we'll grab a fresh one. Again, that x equals 4 is just a vertical line at x equals 4. 1, 2, 3, 4. So if you draw that line here, then that's going to be the end of our limit of integration. Hopefully it's obvious to you that these two functions intersect each other at 0, right? 0 is giving 0, so the blue function hits the origin. And here 0 is giving 0 too, so the red function also hits the origin. So no doubt about it, our other point of intersection is right here at 0. That means when it comes time to write our integral, then this is kind of an easy one. There's only the one chunk of area. It's obviously this area right here. And that chunk of area is going to be the integral that starts at 0 and runs all the way out to not a point of intersection, but this vertical line at x equals 4. So we just stop at 4. That's easy. And we can see that pretty obviously the positive radical is going to be the bigger function, so 3 root x. Then we'll subtract from that the negative radical, so negative root x. And this one, the temptation to simplify is just too great because we're adding, and we're just adding radicals. So this is literally just the integral from 0 to 4 of 4 root x dx. This one is very simple, such that even though the calculator is encouraged and allowed, you could certainly solve this guy by hand, right? If you couldn't, that's a problem. But we have a calculator, we're allowed to use it, so we'll use it. I'm actually just going to clear these out. I don't need them at all, because we know that we're really just integrating for root x. And we know that we're integrating, second calc option 7, from 0 to 4. And getting 21.33333333. So that's it. You can't see what I just wrote. But what I wrote was the integral and its approximate value. So that's it. There's only number 10 left. We can do that one together and then call it a night. I really am out of time. In the interest of getting this out to you guys, I said I would get it out by about 10 and it's already 10:05. I'm not doing 10. You guys have 10 on the answer key. You can figure it out. Have a great night. Happy studying. See ya tomorrow.